Hey, chemistry, it's Monday, April 6th. Good to see you. Or not see you. I'm on page 410. Be there, please. Last time we talked about solubility, the amount of a substance that you can squeeze into a solution before it becomes saturated is considered the solubility. If you look at the green table on the top of 410, you're going to see that solubility, it depends upon the temperature. On the bottom of 410, it says in the top strip, the green, dark green strip, that it's measured in 100 grams of solvent, water. And so, for example, if you take an potassium nitrate, KNO3, right in the middle of the table, do you see it? And you look at how much potassium nitrate can get into 100 grams of water at 20 degrees, it's 31.6 grams. But if you heat the water up to 80, it's 167 grams. It's dramatically more. And that table right there, that green table, if you take a look over here on page 414, do you see that table on the bottom of page 414? Okay, find potassium nitrate. It should be a green curve, a yellow curve. And you can see that the temperature is on the x-axis and the solubility is on the y-axis. It's the same as the table, except you got values in between values on this graph, because the graph is continuous, but the table is not. And so take potassium nitrate and come up 80, hit the curve, the green, yellow curve, and come across. I get about 180. If I go back to the table we were just looking at 80 degrees, supposed to be 167. So I didn't, I just kind of eyeballed it. I wasn't taking my time and being as accurate as I could with that curve. But you could see on that curve, you could get the solubility for 63 degrees. If you come up, go on the x-axis and find 63, come up and hit the yellow curve, and you turn left, and it's going to come over to about 140-ish. If I go back to the table, let's go back to page 410. If I go back to the table, about 60 degrees would be on KNO3, it would be about 110. And that's about what we saw on the graph. So those are the same. Solubility depends upon temperature. It also would depend upon how many grams of solvent you had. If you had 200 grams, everything in this table is twice as much. I think I gave you a problem like that on that last quiz. Okay, so here's the question. Take a look at this solution of salt water. It's been sitting there overnight. Would you say that this solution is saturated? Because you can see stuff on the bottom. It sure is. As opposed to, you see that right there? If I put a little bit of water in there, that water would dissolve that little tiny bit of salt real quickly. And let's just do that. There we go. Got a bunch of water in there. Got a little tiny bit of solute. And that solute is just disappearing before our BDIs. Let me go ahead and stir that a little bit. Goodbye, Charlie. Whoop. Goodbye, Charlie. There's nothing on the bottom. That thing is unsaturated. There's room for more. Okay, set that aside. Now, is salt water going to be a electrolyte? Just to review. Oh, look at that. No kidding. It's a good, strong electrolyte. No kidding. It's a good, strong electrolyte because we got a flashing light with the conductivity tester, the electrolyte tester. All right, next thing. We're going to go to solute-solvent interactions, page 410, red category, red line there, words. Okay, it says that like dissolves like. Do you see that? in the fourth line underneath solute solvent interactions. Like dissolve like means this. If you have an ionic solvent, you can dissolve ionic solids in it. Now, what I meant to say was a polar solvent will dissolve an ionic solute. For example, the salt that we've been dissolving. Salt is sodium chloride. There are other types of salts, but this one that I've been using is table salt, sodium chloride, and it's a solid. And if we put it in water, it's going to form sodium ions that are floating around. We say that they are aqueous, and it forms chloride ions that are floating around. We say that those are aqueous. So if the solution looks like this, water molecule, sodium ions, chloride ions, water molecule, water molecule, water molecule, and there's spaces in between the water molecules. And let's just make it clear here. There's one, there's one, there's one, there's one. And there are spaces where those pieces of this is called formula unit, ionically bonded. So when you pull it apart, and water can do that because water has a positive end and a negative end. We say that the density of the protons is greater over here. We say that the density of the electrons is greater over there because oxygen has some lone pairs, and we've already covered all of that in chapter 6. And so this negative end attracts that positive end of the salt, and this positive end attracts that negative end of the salt, and it pulls it apart. And so water, I say, is electrically sticky. It's a good knife. It'll cut solutes that are ionically bonded together. So this has charges in it, and water has charges in it. This is called polarity, and this is called an ionic bond. And so they are likes. But let's suppose you try to get salt to dissolve in oil. Now, oil is an organic material, came from a living thing. This is vegetable oil. And so as a result, it is it does not form ions in solution. So oil, when you put it in water, will not mix because water is polar and this is not. So let's just go ahead and show you that. You already know this. So I'm going to go ahead and put the oil in first because it looks a little bit more interesting that way. I'm going to use a bigger target because I forgot to bring home my funnels. How long have I been going? I don't even know. I got to quit here soon. Made that promise to you. There we go. There's some oil. And here's some water. Yep, you're right. They don't mix. The oil just came right on up there. And we can go ahead and slush it around. Try to get them to mix, and they won't. They'll separate. Oil and water don't mix. Reason is one is organic material, and the other one is inorganic. The one is non-polar, the oil's non-polar, and the water is polar. So they pull apart like that. They just don't, they form two what we call phases, oil on the top of water. They are what we call immiscible. Immiscible does not sound like not mixable. Whereas water and alcohol, they will mix. And the reason is, even though the alcohol came from some living things, it's got a little bit of polarity. And so it's on one end of it, that's all. And if we take the alcohol, we put it in here with the water. There's the water, the distilled water. Here's the 91% isopropyl alcohol. And do you see where it kind of looks fuzzy up there? Well, no, you can't. Where it looks a little fuzzy up there, well, that fuzziness is going away. And the reason it's going away is because it's dissolving. Yeah, well, alcohol is dissolving because likes dissolve likes. In fact, let's go over to page 412, and then I'm going to come back to 411 later. Liquids is on 412, black print words, of course. Liquids that are not soluble in each other are called immiscible. Toluene and water are immiscible. And then it goes on and says non-polar substances such as fats or oils or greases, they won't dissolve in water because they're non-polar. Water's polar. And it says here they'll dissolve in non-polar liquids like carbon tetrachloride, toluene, and gasoline. And the reason that we can clean oily stuff or grease off our hands with gasoline, it's not recommended, is because they're both non-polar. And so that the gasoline form serves as a nice solvent. Turpentine, that kind of thing, paint thinner, those are all non-polar liquids that serve as solvents, good solvents for substances that come from living things, organic materials like fats and oils and greases. And the reason is because the only attraction between the molecules in both of those cases are the London dispersion forces, which we had talked about earlier. They're very weak. But liquids that dissolve freely in each other are miscible. Benzene and carbon tetrachloride are miscible. Well, they're both nonpolar, they both are the same. So they're miscible. Ethanol and water are miscible. And I would like to talk to you about that. It's pretty interesting. I'm going to go up here to my little table here. Oh, by the way, you want to see something else that's not mixable? I'm going to show you this. This stuff is cornstarch. If I put cornstarch in water, now that's salt water. I don't want you to think I'm trying to pull a fast one on you. Okay. Very slow dissolving process. Look at that. Cornstarch just sitting on the top. If we go ahead and agitate it, it's not going to help a whole lot. It'll try. It'll take a while. It'll get in there eventually, but it's a really slow mix. And so we say that things that mix so slowly are non-soluble. But it's just over a long period of time. But when we talk about miscible and immiscible, we're talking about liquids dissolving in liquids. That's a different deal. That's just essentially not soluble, but it is slowly. Okay, let's go ahead and show you that alcohol thing. I want to show you that before I quit. So ethanol is good old C2H5OH. That's called ethanol. What I always have to do whenever I say that word, ethanol. That's what they drink, you know. Anyway, so carbons always go in the middle, right? And then hydrogen's on the outside, they never go in the middle. It becomes a Lewis structure. Remember that? And so your hydrogens go like that, and you're in your hydroxyl group. Not a hydroxide, a hydroxyl group is appended on the outside of this. And what happens is this. This is highly electronegative. So it's an electron hog. So this little group right here has a positive end and a negative end. It has polarity, but only this portion of the whole molecule has polarity. So because of the polarity, it will dissolve. But the hydroxyl group will not detach. So the alcohol does not form ions in solution, but the polarity will allow it to dissolve in water, which is polar. This is polar on one end, and water is polar, so they will dissolve. Like dissolves like. But because this will not detach, it does not form ions in solution, the alcohol is nonpolar. I mean, is not an electrolyte. You get that? And that's on page 412. Water and alcohol do mix. It's driving and alcohol that don't mix. Don't forget that. That's a funny, laugh now. Okay, so that's page 412. I might even revisit that a little bit to talk to you about sugar also tomorrow. And then 411, we need to do a little more work on 411. We'll do that. Okay. Yeah.